Hello everyone, on behalf of Physics Made Easy Kota, I am welcoming you in our next video lecture on the topic electronic devices. We already study about the extrinsic semiconductor, and we know that extrinsic semiconductor are of two types. The first type is the n-type semiconductor. So how the n-type semiconductors are formed? When we take a pure semiconductor, like we take the pure silicon or germanium crystal of a semiconductor that have the four valence electrons. When these four valence electrons, pure semiconductor, get doped with the controlled amount of pentavalent atoms like arsenic, phosphorus, then we get a n-type semiconductor. So n-type semiconductor only formed when the pure semiconductor is doped with pentavalent atom. In actual, we can understand this from the figure that the four valence electron from the impure atom will combine with the four electrons of the silicon to form the four covalent bond. But the fifth one is not able to form the bond, so it is free to move inside the crystal, and thus each atom of impure substance donate a free electron for the conduction, and hence that is known as the donor atom. Giving the free electron for conduction, the impure atom become positive charge because it arises the hole. Thus, in p-type semiconductor, electrons are the majority carriers that are helpful in arising the hole, and the holes are the minority carriers. We do the doping to improve the conductivity of the pure semiconductor. So what about now the conductivity or the energy band theory? We can compare the doped semiconductor and semiconductor with the pure semiconductor, and in this case the lowest energy level of the conduction band is less. The electrons occupy the specific energy state that is called as the donor energy state. This donor energy level is below the bottom of the conduction band. Thus, we need a very small energy to excite the electrons from the donor energy state to the conduction band, and for this case the conductivity is greatly improved if we compare it with a pure semiconductor. So in this figure, we can see that there is a formation of the covalent bonds in the pure semiconductor. For example, we take a germanium semiconductor. As the germanium have the four valence electrons and all the valency is satisfied. But we want to improve its conductivity more, then we create a p-type of semiconductor. And how the p-type of semiconductor is created? This is created by taking the trivalent atoms. So for the trivalent atom, there are the three valence electrons. So we can see that the three covalent bond get formed and the one bond is not created. So there is the hole at that place, and creating of this hole help in improving the conductivity. So how it is helpful? So we can see that the electron is missing and at that place a hole is created. This hole is compensated by breaking of germanium covalent bond in the neighborhood. That then here the electron get released and this electron try to occupy that space which is vacant. So when this electron move to the vacant space at the position where it is moving, there is a creation of the hole. So in this way, when the electron move towards the hole, it result in the hole formation at some other place. So these trivalent atoms are called acceptor atoms, and conduction of electricity is due to the motion of holes. Again here the hole is greater. Now the neighborhood covalent bonds see this hole and the electron move from that place to cover up this hole. So this result in creation of the hole at the place where the electron is present previously. So in this way holes are moving, and such semiconductor is known as a p-type semiconductor. Holes are the majority carriers and the electrons are the minority carriers. So here we can see the diagram. Here is a valence band and the conduction band. When a pure semiconductor is doped with the trivalent atoms, their trivalent atom behave as the acceptor atoms, and the energy level is created near the valence band. At room temperature, the electrons in the valence band can easily be transferred to the acceptor level. So this produces a large number of holes or vacancies. We can see also as the holes are shown in the circle form, and these holes are created in the valence band. The valence band become the whole conducting band, and hence the conductivity improves. p-n junction formation. P-n junction is the basic building block of many semiconductor devices. Like we can get the diodes, transistors from this. So how to create a p-n junction? First of all, we consider the thin types of the silicon p-type semiconductor wafer, and we can convert a part of the p-type semiconductor into n-type silicon semiconductor by adding a small quantity of pentavalent impurity. So in this way we form the p-n junction in which p and n are combined together. So for the p-type, holes are the majority carriers because the conductivity is due to the motion of the holes, and for the n-type, electrons are the majority carrier because there is a one free electron that may take the initiative to set up the conductivity of the complete system or the impure semiconductor. In n-type semiconductor, the concentration of electron is more as compared to the concentration of the hole. So similarly, in p-type semiconductor, concentration of the holes are more as compared to the concentration of the electron. So the first step that occur in the p-n semiconductor is the diffusion, that the electrons and the holes start diffusing. So in the formation of p-n junction, due to the concentration gradient across the p and the n side, the electrons diffuse from the n region to the p region, and the holes diffuse from the p region to the n region. As there is a difference in the concentration, as in the p-type, holes are in the majority, and for the n-type, electrons are in the majority. So the motion of the charge carriers due to difference in concentration in two regions of the p-n junction, across the junction there is a rising of the diffusion current. As the diffusion continues, it leaves behind a positive charge on the n side close to the junction, and the positive charge is called as the ionized donor and is immovable due to bonding with the surrounding atoms. Similarly, we can see that in the p region close to the junction there is a negative charge or a scepter ions, which is also immovable due to the bonding with the surrounding atoms. So here is a space created. The space charge region on both sides of the p-n junction has immovable ions, and this result in the formation of the depletion region. And the depletion region formation result in settling up a field at a junction. The field set up along the junction act like the false or just as a fictitious battery that is connected across the junction, with the positive terminal connector to the n region and a negative terminal connector to the p region. Some things we have to learn from this creation of the p-n junction. The first one is a barrier creation. The electric field at the junction setups, where that set up a barrier which oppose further diffusion of majority charge carriers through the junction. Thus the barrier get created at the junction that helps to prevent further diffusion. And what about the width of the barrier? The physical distance from one side of the barrier to the the another side, that is called as the width of the barrier. And what is the height? The difference in potential from one side of the barrier to the another side is known as the height of the barrier. Next important thing that we got to know is the drift current. Due to the electric field developed at the junction, the electrons from the p region moves to the n region. Similarly, the holes from the n region move to the p region. This result in the current, and that current is due to the drift, so this is known as the drift current. The motion of the charge carriers across the junction due to electric field, that is called as the drift. Then what is the difference between the drift current and the diffusion current? The drift current is in a direction opposite to that of the diffusion current. At a particular stage, the drift current become equal to the diffusion current. This stage is said to be equilibrium state when no current flow across the p-n junction. Potential barrier become maximum, and that is equal to, we can say, as Vp. There is a p-n junction is called as formation is done, and this p-n junction is under equilibrium as the drift current is in balance with the diffusion current and there is no net current. The N materials has lost some electrons and the P materials has acquired those electrons now. Thus, the N material is positive with respect to the P material. The potential also prevents the movement of electrons from the N region to P region, and that potential is known as the barrier potential. So now some special cases. When doping concentration is small, then what will happen? Then the electrons or holes move a large distance before collision with another electrons or holes. Hence, it will result in increasing the width of the p-n junction. As width of the p-n junction increases, the electric field becomes small. P-n junction diode. A semiconductor diode is called as a P-n junction with metallic contacts provided at the ends for the application of external voltage. That is, we can apply the external battery to the ends of the diode. And the P-n junction diode is a two-terminal device. This is the symbolic representation. Here the P side, that is a whole side, is represented by this symbol and that is taken as positive, and the electron side is represented by the vertical line and that is shown as the negative. These two ends are provided which can be attached to external voltage. There are two methods of biasing a p-n junction. First one, forward biasing. Second is a reverse bias. Forward biasing. Forward biasing is done when we join external battery to the p-n diode. Then the positive terminal of the external battery is connected to the P side or the whole side, and the negative terminal of the external battery is connected to the N side or the electron side. So now what is reverse biasing? Reverse biasing is done if the P terminal of the external battery is connected to the N side and the negative terminal of the external battery is connected to the P side. So we just reverse the connection. Negatives connected to the positive, that is a hole which are regarded as a positive P side, and the positive terminal of the battery is connected to the negative side as the electrons are regarded as a negative or the N side. So this junction, this biasing is known as a reversed biasing. Light emitting diode. A special heavily doped p-n junction which emits spontaneous radiations when it is forward biased. So the use of the LED, it converts electrical energy into light energy. This is a symbolic representation for the LED. Here it represents the P side and the N side and node and cathode along with the symbol of the light. LEDs can be made from the different nature of the semiconductor, like they can be made from the elemental semiconductor and then they emit the energy in the form of the infrared radiations, and those which are created from the compound semiconductor emit energy in different forms. There are the various uses of the LED like in remote controls, virtual RAM system, optical communication. Also some work is doing for developing the white LEDs which can replace the incandescent lamps. Photodiode is also the another application of the PN junction diode, as photodiodes are used for detecting optical signals, or they act as a photodetector. So this is a special PN junction diode that is made up of photosensitive semiconductor material. The diode has a transparent window to allow light to fall on it. Thank you for watching. Have a good day. Take care.